We're going to continue on with chapter 5. Today we're going to be talking about the nomenclature of stereoisomers. So when we're looking at the nomenclature of stereoisomers, we can use the Kahn and Gold Prelog rules. They're also known as the CIP rules. This document right here is going to be in the course documents on Blackboard. So we're going to go through this set of rules slowly, step by step. So this set of rules assigns a priority to each atom or even substituent bound to a stereocenter. So remember, stereocenter is a carbon atom that has 4 different substituents attached to it. So today we're going to be talking about only tetrahedral carbons atoms. Next lecture will be on something that's containing a double bond. So when we're using the CIP rules, a specific configuration will be assigned. So we're going to have 2 different types of configurations that we're going to talk about. So we're going to have an R configuration and a S configuration. So what this is really telling us, this is telling us the permanent geometry, which is going to be defined by the spatial arrangement of the atoms. So let's look at the actual rules, the CIP rules. So the first rule that we're going to look at, so atoms with higher atomic number have higher priority. So if we're looking at an isotope, the isotope with the higher mass will take priority. So let's look at a few examples. So if we're comparing carbon versus hydrogen, carbon would take priority over hydrogen. Nitrogen versus carbon, nitrogen is going to take priority over carbon. Again, we're just looking at the atomic number of both of these atoms. Bromine versus chlorine is going to have a higher priority. Sulfur versus oxygen, deuterium versus hydrogen, and phosphorus would have a higher priority versus fluorine, and then magnesium would have a higher priority than something like lithium. Rule number 2. So if there is no difference between the atoms that are directly attached, what we're going to do is we're going to move down the chain. So what we're really going to be looking for is something that we can call a tiebreaker. So we're going to move down the chain of each substituent until a tiebreaker is found. So let's look at a few examples. So if we have some chain that is the same, so this just indicates right here that there's some chain, and then we have this group here versus, again, that same chain attached to this group here. So this carbon is attached to 2 hydrogens and a chlorine. This carbon here is attached to 3 hydrogens. So this compound here is going to take priority because of the chlorine versus the hydrogen. If we look at another example, again, we have some chain, and then we have this substituent coming off the chain versus that same chain with this substituent coming off. So what we're going to look at is each of them have 2 bromines. The difference is this one has a bromine attached, this one has an iodine attached. So this one would take priority just again because of the higher atomic number. If we're looking at this example here versus this example here, so in this case we have one hydrogen, in this case we have two hydrogens. This carbon here is attached to two carbons, where this carbon here is only attached to one carbon. So this one here would take higher priority. If we're looking at something like this, so we have again some chain, we have a CH3, CH3, and a sulfur, versus something like this. So when we're looking at this carbon here, this carbon is attached to a carbon, and a sulfur. This carbon here is attached to a carbon, and a carbon. So this group here is going to take higher priority because we have a sulfur versus a carbon. So this is, I should mention right here that you want to make sure to take note that this doesn't mean the overall heaviest substituent takes higher priority. Again, we're just looking at what this stereocenter is directly attached to. All right, let's look at another example. If we have some chain and then we have this versus another, the same chain versus something like this. So we have the chain, then we have a carbon, so these groups are the same. Move down, we have this carbon, we have this carbon, and then this carbon is attached to an oxygen, this carbon is attached to a carbon. So again, higher atomic number is here, so it would take higher priority when we are comparing the two. Another thing that needs to be mentioned with these rules, if we're looking at multiple bonds, we're going to count each bond as if the atom in question were bonded to separate atoms. So we'll look at some examples. So if we look at, so again, we have some chain, then we have this group right here. What we're going to do is kind of think of it as break and duplicate. So we have this carbon here. So again, we have the chain. We're going to break the pi bonds and then we're going to duplicate. So we have 2 pi bonds. So we're going to add 2 additional carbons, which I circled. And then we have, so think of this one as coming from like the sigma bond. And then these ones that we're breaking and duplicating are coming from the pi bond. So if we look at this versus say something like, so we have this chain here, then we have something that looks like this. So same idea here, we're going to break the pi bonds and duplicate. So we're going to have that chain and then we're going to have a carbon. We have this carbon coming from the sigma bond, and then we're breaking that, we're thinking that we're breaking that pi bond, which is this carbon that's circled. So this is coming from the pi bond. And then we have a hydrogen. So this carbon here is attached to a carbon, where this carbon here is attached to a carbon, hydrogen. So this compound here would take higher priority when compared to this compound. Let's look at another example. So we have, again, some chain, then we have this molecule here, and we're going to compare it to this molecule here. So when we do the comparison, we notice that we have a pi bond here. So again, we're going to think we need to break that pi bond and duplicate. So when we do that, we can think of it as So again, this one would be coming from like the sigma bond, and then this is the one that we're thinking about as breaking and duplicating. So this is coming from the pi bond. So this carbon here is attached to an oxygen, oxygen, oxygen. When we look at this compound right here, what we have is we have a carbon attached to an oxygen, and a hydrogen. So when we're comparing this one versus this one, number one is going to take higher priority, again, just because of that carbon being attached to 3 different oxygen atoms. So why is all of this important? So when we're defining stereocenters using the CIP rules, so again, we're talking about tetrahedral carbons right now. So for a tetrahedral carbon, you are always going to place the lowest priority away. So just a quick refresher, away is always going to be the dash, which means it's pointing like into the paper or going back. So if the substituents, so number 1, 2, and 3, 1 being the highest priority, 3 being the highest, or sorry, 1 being the most highest priority, 3 being the lowest priority, is clockwise. So clockwise, I'm just going to show as CW. Then it's going to be an R configuration. If the substituents, so again, 1, 2, and 3, 1's going to be our highest priority, 3 would be our lowest priority, is counterclockwise, it's going to be an S configuration. So let's look at a few examples. So if we look at this molecule here, so what we're going to do is we're going to number all of these by priority. So this one is pretty much just smaller substituents or just an atom, so this one's a little bit easier to look at. But what we want to do is we want to think about atomic numbers and what this carbon's directly attached to. So first we would have this as our highest priority, bromine would be our second priority, this CH3 group would be 3, and then our hydrogen is our lowest priority. And again, we always need to make sure that that lowest priority, so number 4, is always pointing away or pointing into the paper, behind the paper, which it is in this case. So now we're going to look at our numbers. So we're going from 1, 2 to 3. So we're going clockwise, which means we have an R configuration. So let's think of the enantiomer. So again, we talked about this last lecture. So we're going to look at, have a mirror plane. And when we draw this, we're going to have something that looks like this. So again, we'll number the priorities, going by atomic number, or what that carbon at that stereocenter is directly attached to. Again, our hydrogen is pointing into the paper, which is what we need, the lowest priority pointing into the paper. So now we will notice that we're going counterclockwise. When we're going counterclockwise, we have an S configuration. So this is what you'll notice when you are looking at 2 enantiomers. One would be the R configuration and one would be the S configuration. So something to kind of help you guys out, if the highest priority is not pointing away or kind of into your paper, then you just flip the assignment. Meaning if it would be an R configuration, but that lowest priority is not a dash, then you're just going to flip it to an S configuration. So let's look at this example here. So first thing you want to do is just number them as we did on the first example. So number 1, then we have 2, then we have 3, then we have 4. But we will notice that the lowest priority, so hydrogen, is not pointing into the paper. So it's not a dash. So when we look at this, we have 1, 2, 3, so we're going clockwise, so that would give us an R configuration. But again, because that hydrogen is not pointing into the paper, what we're going to do is we're just going to flip the configuration. So this would actually be an S configuration. So again, it's really important to make sure that you're looking at the lowest priority and it's always behind the paper. If it's not behind the paper, then what you're going to do is or into the paper, sorry, I should say, then you are just going to flip the assignment of the configuration. So let's look at an example, kind of a more complex example. So if we have something that looks like this. Sorry, this pen I'm still getting used to. All right, so we have something that looks like this molecule here. So 1 and 4 are pretty easy, right? So this one would be the highest priority because it's attached to a nitrogen. And this one here, this hydrogen here, would be our lowest priority. So now we have to look at this group here and this group here and kind of think what is it attached to. So if we think about it, we have something that looks like this. So this group here we'll call little a. This is little a. Then this group here we'll call little b. So this is going to look like something that looks like that. So now we want to look at how each of these atoms are connected. So if we number this one right here, A, so this carbon here and this carbon here. So what we're going to think about is, remember, you have to think about that break and duplicate. So this carbon here is actually attached to this carbon coming, again, think of it coming from like the sigma bond, and then we're breaking that. So we have 2 other carbons generated. And then what we're going to see is we're going to see the same exact thing for this carbon here. So we have a pi bond. So this is coming from the pi bond when we break and duplicate, but we also have a carbon here and a carbon here. So when we look at, we'll call that big A, it's connected all carbon, carbon, carbon. So now if we look at B, so this would be capital B, this would be capital B. So capital B, it's going to be a carbon, 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 hydrogen in both cases. So again, think about it. It's a good practice. Try to think about breaking and duplicating it and make sure that you're seeing that that carbon is attached to carbon, 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 hydrogen. And then when we look at C, so C is really just going to be this last group right here. So we have a hydrogen versus a CH3 group. So the CH3 group is going to take priority over a hydrogen because, again, higher atomic number. So that is going to make this one right here number 3, leaving this, this one number 2, and this one number 3. So we have 1, 2, 3, right? So we are going in the clockwise direction. So that would give us the R configuration. But what you'll notice is our highest priority, sorry, I keep saying that, our lowest priority is not in the back. So we will flip the configuration. So that would mean that this has an S configuration. Let's look at something with more than one stereocenter. So if we have something that looks like this right here, first thing is you have to identify your stereocenter. So we have a stereocenter here and we have a stereocenter here. So now that we know where our 2 stereocenters are, now we have to think about the configuration. So is it R or S configuration? And again, we're just going to think about priorities. So we have this right here is going to be our first priority, so nitrogen versus basically a carbon, or a hydrogen. Our number 2 priority is going to be right here because we have a carbon which is attached to an oxygen and then another oxygen. This would be our 3rd priority, this methyl group right here, and then our 4th priority would be our hydrogen. So looking at this, we have 1, 2, 3 counterclockwise. So that is going to be an S configuration. So our hydrogen, which is our lowest priority, is in the back, which is what we want. So we can leave it as the S configuration. When we're looking at this stereo center right here, we have, again, nitrogen is going to be priority number 1. This would be number 2. Our methyl group would be number 3. Our hydrogen would be number 4. So here we have clockwise, which would give us an R configuration, but the lowest priority, so that hydrogen, is not pointing away or into the paper. So we have to flip. So that would mean that this would be a S configuration. So a lot of times you'll see it just written right at that stereo center. So we're going to stop right here. Again, look over the Con and Gold pre-log rules that are in the course documents.